see it. We will be meeting in the library on Thursday. I just got the room number, LIB 120. So what I want you to do is do that pre-reflection or pre-assignment thoughts. So in that little handout sheet paper, I just copied and pasted this text out of it, okay, up onto the slide. So just kind of put down at minimally some notes. Ideally, we're still sentence and paragraph formation, but some notes on what you already know or think you know about genetic information, and potentially even how some of that stuff was discovered. Okay. This is not a right or wrong thing. This is just, let's get a baseline on what you already have kind of built up. Okay? Make sense? Questions about it? Yeah.
And this isn't anything specific to whichever topic we use.
This is not necessarily specific to whatever topic. Along the lines of topics, as Robin already asked, do you have to pick one prior to the library visit? No. Okay. So if you already know a topic, you're like, I want to do this, that's fine. You can call dibs. Okay. No more than 2 people per topic, but when you call dibs, then somebody else could join you. Other questions? So many options. There's what, 5? Yeah, it shouldn't be too bad. Yeah, and some of those projects are kind of grander scheme details of genetic information. They aren't getting into the nitty-gritty detail. For instance, Kornberg is going to be a lot more the nitty-gritty detail, what's actually happening during DNA, what did I say, replication or transcription? Transcription. So he did a lot of research with actually nailing down what's happening in each of those stages. The other ones tend to be kind of the larger picture of genetic information. Okay? So, we ended on the fun cliffhanger of where do we determine some of these values. So when we go through and deal with our Michaelis-Menten expressions, so ultimately this standard enzyme reaction was all Michaelis-Menten kind of solved. They went through and determined this, and they were able to boil it down to pretty much 2 factors that you could use to describe an individual enzyme. We have Vmax, and we have Km. Okay, capital M for our Michaelis-Menten expression. Okay. After that, the only thing we really care about is how much substrate is present. And we would end up being able to predict something about our enzyme activity by looking at our Vmax and Km values. So by doing a plot like we've got here, we can conclude some information about what our enzyme is doing, and we can get some kind of useful information. So Vmax is what? Okay. It's the max. V would seem to make sense to stand for velocity. We're really looking at the rate, okay, for our enzyme reaction. And our Km was what? We'll come to that in a second. That's how we would solve for it. This is really kind of put in quotes because it's not exactly true, but it's pretty close. The binding affinity of your enzyme for the substrate. So the larger your Km, the tighter the enzyme grabs your substrate. The smaller the Km, the looser it grabs it. Okay, so that gives us some general information about what the enzyme can do. We can bring in other information like turnover number, which is a relationship between your enzyme concentration and your Vmax and all that fun stuff. But those are our primary values that we would report for an individual enzyme, and that gets us a sizable amount of information about its how it works and how fast it works. Okay, so the next part is how do we get those values? Okay. If we take a look at a plot of your rate versus your substrate concentration, believe it or not, we can get all of those values, both the Vmax and the Km. Okay. The easiest one to determine was the Vmax. Where did we determine our Vmax? Yeah, it's where it flattens off. Okay, officially, it's an asymptote, meaning the curve will never hit perfectly Vmax, but it gets infinitely close. So there's our Vmax. So by interpreting our curve, if we've got enough data points, we can actually predict what the Vmax is. Okay. That does assume that we've run enough of an experiment or enough different rates versus concentrations that we actually see it level off. Okay. If, for instance, we only plotted enough data to be, say, maybe the 3 data points that I'm drawing in now, down at the bottom, we don't see it level off, which means it's going to be very difficult to predict Vmax. Okay. So the only way we can get Vmax off of an experiment like this is that we run enough data that we can see it start to level. Okay. That allows us to get Vmax. And we'll talk about that big kind of restriction on interpreting our Vmax from our data, because that means a lot of data needs to go into this. Km can also be interpreted off of this. Okay, and one of the ways that we could go through and do it is rearrange our equation to solve for Km. If I can do this right, we get Vmax times our substrate. Jiminy Christmas. That guy is freaking out over there. Minus our substrate. I'll do that right?
Yep.
Okay. So when can we determine our Km? So Jimmy, you started to suggest something. What did you suggest?
Just from the book, Vmax divided by 2 gives us our Km.
So if we just divide Vmax by 2, that's not going to get us our Km per se. Okay. It's actually coming back to something else.
The order of the...
Okay. Vmax and our V are our rates, our individual
And
expressions.
V was in the middle of the curve. And didn't you say that the order of the reaction was...
If we substitute for V, okay, so we know what Vmax is, it's a constant. If we substitute for V, 1/2 Vmax, what happens?
That should be V.
So the Vmax cancels, and we'd end up with what? Doing the algebra, theoretically you should be able to do that in your head, but if you don't, that's okay. 1 divided by 1/2 is 2 times the substrate concentration minus the substrate concentration, which means Km would equal careful,
No, it's just S.
just S. You got it now?
2s, oh yeah, there.
Yeah, it's okay.
One of those.
So what we're saying is when we go to a rate that is 1/2 Vmax, the substrate concentration at that point
I'll tell you what it is.
is your Km. Similar kind of concept to at the half equivalence point, pH equals, ouch, at our half equivalence point, our pH is equal to
pKa.
our pKa. We're getting the same kind of idea here. Okay, at our half max, the substrate concentration is equal to our Km. This allows us to look at a curve, and we can now predict our Vmax. We can also predict our Km. Kind of neat. Okay, you are expected to be able to do this. Okay, how and why are you expected to be able to do this? Ultimately, what it comes down to is now just memorization. You know where Vmax is, you know Km is at half Vmax. Okay? So you aren't expected to derive any of that, and you're now just told you have to have it memorized. Okay? So that is helpful if we have this whole plot. Okay? But what happens if, say, when we run our experiment, and instead of having that nice big curve of all of that data, all we have are, say, those data points. Well, if we have 4 data points, we could try and fit this to the equation of that exponential line not sure it's exponential. Maybe it's logarithmic. Whatever it is. We could just say, oh, we know it's supposed to fit this line, so I'm going to force it to fit to that. Well, but then you're saying that it's supposed to fit to that. You're making up data or making up your fit to match your data. And that's bad science. Okay? So to get it appropriate where we can determine our Vmax and Km, we would need to run more experiments to get that flat line curve so that we could then match our curve perfectly to that line. And we can do that with technology today. Okay? We've got people that we can pay next to nothing for to run our experiments, to do a whole bunch of data plots. We then have the computer technology to be able to fit all of those individual data points to that curved line and be able to determine Vmax and Km. Okay? However, that was assuming we had a whole bunch of people that we could rely on and that we had the computer programs to be able to fit that graphical analysis. Okay? This stuff was done early 1900s. We don't have the maximum amount of people to be able to go through and do this, and we don't have the computer programs that can fit those curves. So what do we do instead? We can do still our individual experiments, but again, we don't have enough people to plot enough data to get a reasonable curve. Okay? And that's the issue that we would need. Even if we did get that, we don't have the ability to now graphically analyze to fit or get the equation to fit that line to determine your half Vmax and all that fun stuff. Okay. Well, what was initially done is we take the data and we come up with or take our expression and we say, there's got to be a way that I can reformat that equation so that it matches a straight line. So how can I rearrange the equation that's represented in this line, change the variables around without changing their meaning to get the equation of a straight line? Well, what's the equation of a straight line? Y equals mx plus b. So we'd have to somehow switch this around into that format so that we can interpret it appropriately. Okay? And it's clearly obvious on how you would go through and do that. I'm kidding. It's not clearly obvious. Okay. This was done. Okay, we did it in 152. A lot of the chemistry you do in 152 is rearranging your equation to get into an equation of a straight line. It was easier in 152. It's a lot harder here. Okay. If we take the reciprocal of both sides, we can end up with this expression. 1 over our rate will equal our Km over Vmax times 1 over the substrate concentration plus 1 over Vmax. Okay. This does now fit the equation y equals mx plus b. Would we still have the data to be able to plot this? Well, v is our velocity, our rate. Whoops, sorry, I got to go back a little bit further. Our rate. Okay. But instead of plotting it versus rate, we'll plot it versus 1 over the rate. Okay. So we can plot that value. When we run an experiment, we can get that data. Okay. If we move to the next part, we don't have Km, we don't have Vmax. That's part of the whole solving process. So there's no way we'd be able to plot something for that. Okay. But 1 over the substrate concentration. We need to know the substrate concentration to predict our rate or to determine our rate for an individual experiment. So we'll know the substrate concentration. So we'll plot our experiment 1 over rate versus 1 over the substrate concentration. Okay, so those are my x's and y's. When I plot this out, my curve, instead of being this nasty curved line, will now get plotted as a straight line. Okay, and in that straight line, it's our y-axis, 1 over our rate, our x-axis being 1 over our substrate concentration. We can then interpret the equation of the line to come up with some interesting terms. Number 1 over Vmax is equivalent to b. What was b in the equation of a straight line? The y-intercept. On my curve, I can now go to the y-intercept, and that point is now 1 over Vmax. I can solve for solve for Vmax by looking at the y-intercept and taking the reciprocal of it. I now have Vmax.
You can plug it in.
Once I know Vmax, I can then plug it into the equation to determine what Km is from the slope of the line. Because we know m is equal to our slope. So when we solve for the equation of the line, we'll know the slope, we'll know the y-intercept. It's now just a question of algebra and substitution to determine what your Km is and to determine what the Vmax is. The reason this is powerful is, again, to generate our standard enzyme curve, the one shown in red, we'd have to have enough data points to get all of that out, okay? Which could be hundreds of thousands of data points. That's a bit difficult if we only got 2 people doing the experiments. Okay? Now with the Lineweaver-Burke plot, we can do maybe 10, 20 data points. So we still have a significant amount of data, but 10 or 20 experiments, you could probably get that cranked out in a couple days. With that information, I could just have, on my red line, just the data for that. But when I go through and now convert it into Lineweaver-Burke, I have the equation of the straight line. I can determine what Vmax is. I can determine what Km is directly off of my purple curve. Kind of neat. Make sense? Okay. So you are responsible for being able to determine these things in the variety of fashions that we've got. Okay. I could give you, oh man, I'm going to go back a whole lot. Too far. I could give you this curve and say, okay, with this curve, tell me what Km is. Well, we know Km is 1/2 Vmax. Okay. I could also give you the curve. This would be really mean, so I wouldn't do this. Okay. Where I said rate, and I said substrate concentration. Said, tell me what Km and Vmax are. Well, how would you go through and do that? That looks like a straight line. We have no idea where it levels off. So what do you have to do?
The straight line is the linear version.
The linear version was only true if I plotted 1 over rate, 1 over substrate.
Oh, no.
So how would you have to do this? You'd have to take each of those data points, figure out what their rate was, what their substrate concentration was, do the inverse, then plot. Then you're in the Lineweaver-Burke, then you can look at the equation of the straight line. Nasty. I would never do that. Okay. But what I could do, okay, which is much more likely, is give you the 1 over rate, 1 over the substrate. With that data, you would extrapolate your line through roughly. This point was where it crossed your y-intercept.
1 over Vmax.
1 over Vmax. You could then tell me what Vmax was. And then you could tell me by then determining what the slope of that line was. Y equals change in y over the change in x, which is equal to Km over Vmax. Because you know the y-intercept is Vmax, or what the y-intercept is, you can plug in and you can solve for Km.
Okay. You would actually give us numbers for that?
I would have to give you, well, I don't necessarily have to give you numbers, because I would probably give you numbers to make the calculation of change in y over change in x more reliable, so that I could just look at your answer numerically to say it's right. If I didn't give you numbers, you would then have to just generate an arbitrary number scale and try and evaluate based off of that number scale. Okay. Worst case, what you would probably see would be markings, rough markings, saying that 1 over substrate went up to 10, and this was 0. You could then approximate and say we're roughly halfway in between. This is at 0.5. Whoops, that's not 5. Halfway in between. That first one was 5. Next one was 2.5. Next one was 1. Right? And then the y-intercept I'd have to give you, or the y-axis, I'd have to give you another number up here. Let's say 10 again. Why not? So that first one was 5 and 7. Next one was 2.5 and 5. Last one was 1 and 1. You'd be able to calculate by approximation off those numbers. I'd have to give you some kind of scale. Make sense? Okay. That's getting pretty nasty into the calculations. More than likely, you'd be given some pretty solid numbers to be able to do some predictions.
So you give us a number like diagrams?
I could give you with all those numbers, yeah.
Those numbers would have to figure out KM and Vmax.
KM and Vmax, and you should be able to do that from that. Okay, questions about that? Because now is the time to bring up the questions, because it really gets worse from here. Okay.
So I would probably get into this, but what do we use this as?
So Km tells us something about the binding affinity for an individual enzyme for a substrate. So that allows us to now conclude something along those lines for that enzyme. So we could then tabulate, look at enzyme activities, or look at enzyme names and say, oh, well, the Km is this value. That means it binds tighter than, say, this enzyme. So it's a way of just tabulating your numerical results. What are you specifically going to use it for in this class? Nothing. Okay. You're just trying to determine what those values are. Because if you moved further into biochemistry, you'd then be saying, okay, what enzyme do I want to use to do this reaction? Okay. Or if you wanted to manipulate certain enzymes to do things, you could start to say, well, how can I change Km? What's that going to do to the rest of my reaction? So it's looking at tabulating results of enzyme activities. Okay. Same deal with the Vmax. It's giving you some information about what the enzyme can do. If you were to then use that enzyme, you can then predict something about where it's going to go, how fast it's going to react, all that fun stuff.
The concentrations of the concentrations first.
To get it in an appropriate time, yeah.
So why would you want an enzyme with a different affinity one way or another? Like what, it depends on whatever experiment you're trying to run? Or?
Yep.
I was going to ask, is the higher KM more affinity towards something? Or?
The higher the Km, the larger. Oh, crap. I think I said the larger the binding affinity, but I'm starting to think that's backwards. I think it's smaller. Because Km is K2 plus K minus 1. Okay. And those are the dissociations. So the larger the Km, I think the less the binding affinity, but this is one that always gets me confused. And you're looking at it, it should tell you, oh yeah. I'll pause this, we'll have to listen to sign. So your Michaelis-Menten took this information and was able to then take all of those K1s, K minus 1s, and all that fun stuff. That was what we looked at all the way back up. You know, all the way back. Okay. Oof. We started with this expression with Michaelis-Menten. They said, okay, how can we possibly solve for our rates? Okay, come up with an expression for this. Well, they went through and looked at it. At low substrate concentrations, your rate is very, very slow. Okay. In all cases, it's going to be dependent on K2. So this comes from 152. Our slowest step is going to be the formation of our product. Okay. Enzyme plus substrate, they're just weakly coordinating with each other. To make the product, we're actually changing bonds. So we would predict K2, okay, the formation of our product, to be the slow step. Okay. Your rate will always be dependent on K2. So in both cases, dependent on K2. At low substrate concentrations, your rate is going to be incredibly slow, and if we look at our curve, do I have my curve back here? I don't have my curve back here. At low substrate concentrations, so this was our, come on now, our curve of rate versus substrate. At low substrate concentrations, we're down here. What's your rate? Your rate's going to be very, very low, okay, or slow. Okay. That is going to be dependent on our K2. It's dependent on K2 because that is our slow step. Okay. But the concentration of what is going to determine your rate. Okay. If it's the substrate, okay, what we'll remember, this first step we're assuming happens at a fast equilibrium. This is one of our assumptions that we have to make this equation easily solvable. If it's happening at a fast equilibrium, with such low substrate concentration, it's not really going to have a huge effect on our reaction because there's such a small amount of substrate that more than likely it encounters the enzyme and immediately binds the enzyme. So our low substrate concentration then effectively becomes the enzyme substrate complex. Okay? That is then going to be the concentration that's going to determine the rate at low concentrations. Not so much our substrate. Because our concentration is so low that the odd that we'll find substrate on its own, very, very limited. It's going to encounter the enzyme, boom, we're in the enzyme substrate complex. Okay? At high substrate concentrations, now what happens? Okay, well, if we look at our curve, does the rate depend on the substrate anymore? No, it's completely irrelevant. So now I don't care about the substrate. If I don't care about the substrate, I'm also not caring about the enzyme substrate complex, because the enzyme substrate complex requires the substrate. Okay. What is going to determine when that reaction flattens off? How much of the enzyme was actually present to begin with? Okay, or it's not present to begin with, our total enzyme concentration. So our rate then becomes K2 times our total enzyme concentration. We could then attempt to solve each of these equations on their own. Okay? So at high substrate, I can determine the rate by monitoring the concentration of one of my species. Okay? I know the enzyme concentration. I could determine K2. Okay? That's relevant, sure. Now I know K2's value. But what about at low substrate concentrations? Would I be able to solve for anything in that? No. Okay. I'm kind of stuck. There's nothing there's nothing I can really do to monitor that. Okay? Because it's dependent on the enzyme substrate complex, which I can't monitor. So I'm kind of SOL there. So what Michaelis and Menton went through and did is said, okay, let's start to make some assumptions and figure out what we can do with this. We know that at equilibrium, our first step, the rate of the forward, okay, the formation of our enzyme substrate will equal the rate of decomposition of the enzyme substrate. So we're using our equilibrium dynamics to figure that out. We can then set our equations equal to each other. Okay. So what we're assuming is a steady state. We give our reaction enough time that it can balance out and it achieves its equilibrium. We can then rearrange that. We end up with that fun little expression. We can then go through and also take the information that we know about our enzyme concentration. And that's one of the things that makes this complex, is your enzyme concentration is constantly changing, going both up and down, depending on where it is in the reaction. Well, that enzyme concentration is going to be dependent on how much enzyme you started with versus how much is in the enzyme substrate complex. You take that information, substitute it back in, and you end up with this fun expression. The Km is merely just a way of looking at the relationship of those rate constants, okay, which we later said was then the binding affinity. The larger the Km, the lower the binding affinity, because K2 and K minus 1 become smaller values. Okay. Once you've got that, then you take this information, rearrange to form your enzyme substrate concentration. You can then plug that back in to those rate expressions that we were looking at. Okay. And we could do it with the rate being high. Okay. But if we plug in, I didn't do all that. I did it by hand on Thursday. You plug those in, set up your relationships, and you end up with the Michaelis-Menten expression. Okay. So they put all of that together so that we can now come up with tables of data about our enzyme that we know how fast it's working. The idea behind all of science is to figure out how it works, because once you know how it works, you can start to mess with it and make it work better or worse. Okay. Would we want our reactions to work better? Well, if I'm trying to make something, I want it to work as fast as possible. If I'm trying to make a drug to stop an enzyme from working, because maybe that enzyme causes cancer, I want to know how it works so that I can stop it. Okay. So we have to have some information about how it's working and how fast it's working, because then we can modulate and change that in an actual environment. Okay. That's when we then bring in all the meaning of what all those things were. Back to our writing assignment. How do we interpret those off of our curve? Okay. How could we rearrange our curve or rearrange our equation so that we don't have to interpret or have enough data to interpret this?
So are we not going to be doing much with that original equation then? We're pretty much, like, it's just there to kind of explain how we get
Yes,
equation?
exactly right. So the exact equation on how we come through with all this, we don't really use so much. We're more concerned about the end results. Okay. If you were a biochemist, you're going to need to be able to process all that. If we were in a lab, you'd need to be able to use that equation so that you could process and determine this. Okay. But for the sake of the lecture, all you really care about is what results can you pull out of it. How can you tabulate and come to those answers quicker? Kind of makes sense? Make a little more sense now, at least?
Yeah.
I know, it's not super
You're reading through
satisfying.
the book and it's just like, it just keeps jumping to this, to this, to this, to this, and like, you know,
And
back together that moment.
I would agree with it, and I think they skipped a ridiculous amount of steps. When we go back and look at kind of how I went through and solved this section, they just kind of say, oh, you have this equation, and then you just put them together and it's done. Like, well, how did you do that? Okay. And to me, this took me a while to go through and set up so that I understood it and could explain it. Okay. The next part, where we then look at, what happens if we have an inhibitor? How does that change our enzyme dynamics? Okay. The textbook goes through and attempts to explain this as well. Okay. They don't explain any of the mathematics behind it. They kind of just show you some equations and say, oh, this is kind of how it works. Okay? I've tried to go through and deal with the mathematics, and I'm not good enough at it to be able to explain it well enough to you. I would also then potentially argue that you don't need to know the mathematics to be able to understand what you're trying to get out of it. Okay? And I would also argue that you probably don't care. Okay? So it's kind of outside the scope of what we're trying to get in the class. We're trying to get a basic overview so that you can then interpret what those things mean. So if you're going into either pharmacy or PA or med school, they do ask questions about KMs and Vmaxes and what do they mean and can you find them off of a graph. Okay? They don't ask you to solve for it from your initial principles. Okay? So it's more that kind of graphical interpretation. That kind of makes sense? Okay. I did just hand draw one. But this is kind of something that you could see off of a test, would be where on this line can you interpret information. Okay, so I could just give you a line like this, okay, and you would have to say, okay, where can you get information from it? Okay, well, seeing that it's 1 over rate and 1 over substrate means we're looking at the Lineweaver-Burke plot. And the Lineweaver-Burke plot, what does that mean? We have a straight line. The y-intercept was 1 over Vmax. Our slope was that says max. And our slope was Km over Vmax. Okay. So it's using that data to be able to predict some information. What if I had instead given you this line and I'd written rate here? And actually, why not? 1 over substrate there. What would your interpretation be? Our relationships are either rate versus substrate or 1 over rate versus 1 over substrate. So rate versus 1 over substrate, we got really nothing that we can conclude on that. So we wouldn't be able to do that analysis. What if I'd given you 1 versus the, or rate versus substrate? Okay, well, number one, that curve probably wouldn't be given to you because
We don't know if you.
would we expect the rate to be non-zero at a substrate concentration of 0? No. If there's no substrate, the rate shouldn't happen. Okay? So this curve would be wrong, and the curve that you would see instead would be this one. And then it's okay, where do you interpret from this?
You can figure out Vmax.
You can figure out Vmax. You can still figure out Km and all of that stuff off of that curve. So it's looking at what information is given to you and then interpreting based off of, are you looking at standard Michaelis-Menten or are you looking at the Lineweaver-Burke plot? All of that information is available. It just comes down to when you want to use particular sets of data. Okay? The standard Michaelis-Menten that we're looking at right here, being able to interpret this, that should actually go all the way to the 0, sorry, okay, is not an easy curve to interpret, okay, because we very rarely get enough data that we could pick up that curve perfectly. Okay. We're showing it initially because that is the theoretical aspect to it. We used that theoretical aspect to come up with the Michaelis-Menten expression. Once we have the Michaelis-Menten expression, we can convert it into the Lineweaver-Burke that can then plot and allow us to interpret relatively quickly and easily. Okay, kind of makes sense?
Do we use the x-intercept to find the Vmax?
You'll notice that I erased a line and there's an x-intercept there. Okay. We could go through and solve the algebra on what that x-intercept is, or you could just look at what they're telling you it is and it's negative 1 over km. Why does it have to be negative? Okay. We're passing the 0 on our y-intercept, so it will be a negative value, but km should always be positive, so we have to say our x-intercept is a negative 1 over our km. How could we determine that? It's the equation of the straight line. You could see solve for what the x-intercept was from your equation. Okay. Do you want to do that? I don't know. It's up to you. If you care to find that useful, go ahead and do it. It doesn't
If
hurt.
you had the x-intercept, then you could find km pretty easily.
Yeah, but if you have the y-intercept, you can still determine km pretty easily through using the slope. So it's another way to determine the km.
Less easy, though, doing it that way.
It does involve more calculations going from the slope,
But you're gonna
so
have
it
to
just
know the
depends.
slope
Yeah,
anyway. To figure out the x-intercept, you have to know the slope if you
Yep.
weren't given it,
yep.
right?
So it just comes down to what you see as being easier to interpret the information from. Okay. The standard ones that we look at, why we go to y equals mx plus b, is your y-intercept and your slope, because those naturally fall out of your equation of the line. The x-intercept you can solve for, but it's not directly in your equation. Okay? Questions about that?
On the test, were the questions about the graph in the multiple choice area, or the
They could show up in both places. The multiple choice is more likely, because I freely admit it is a confusing topic, and if it's verging outside of my realm, it's probably way, way, way outside of your realm. I don't think it's fair to ask that. Okay. You can take a look at the graphical interpretation is something that can show up anywhere. How you would get to that graph is probably something I wouldn't ask. Okay. So we ready?
Oh, let's go.
Okay, let's try the next part. So what happens to our kinetics if we have an inhibitor? Okay. It's going to make things all sorts of messy. Okay. Add to that fact that, well, actually, let's just remove that. Let's just say we have an inhibitor. Okay. So we've got our normal enzyme function. Okay. Enzyme plus substrate goes to the enzyme substrate complex, and in equilibrium, fast equilibrium, the enzyme substrate every so often can go to form product. Okay. If we now add an inhibitor, okay, so the standard inhibitor to look at would be a competitive inhibitor, okay, but arguably our easiest one to look at. So what we're showing in that diagram is now something other than the substrate is binding to the active site. Well, if it binds to the active site, can the substrate bind to it?
Nope.
Nope. What does that mean happens to the rate of the reaction?
Goes down.
We would expect the rate to change.
Change
Okay.
0.
So now the question is, how does the rate change?
Depends on the concentration of competitive.
It's going to depend on all the concentrations of all the individual species in here. And remember, the two things that we're concerned about are our Vmax and our Km. So when we're now adding our inhibitor, what we want to be able to do is to predict what changes would happen to the Km, what changes would happen to the Vmax. I would argue Vmax is easier to interpret. So let's stick with that. How does our equation change? Okay, and the equation I'm referring to is the one in the box. And I have to erase that bottom line for how it changes. What's changing?
There's not going to be an, I don't know.
Well, we can still potentially form product.
well, no, the rate of the kilo is what I
Okay.
was okay too.
Where does the inhibitor show up?
In the reacting side.
Okay, which reactant side? Because we have a reactant, we have a reactant, and we have a final product. Our inhibitor will only show up on the first part. It won't show up in the enzyme substrate complex because
Because then it's already bound to the.
they're competitive inhibitors. Okay, the inhibitor can't bind the enzyme substrate complex because the substrate's filling the active site where the inhibitor would bind. Okay, so we're adding our inhibitor here. Okay, how does this change the complexity of our reaction? Well, now we have another option. We could form the enzyme inhibitor complex. Okay, so we could call this, say, Ki. Yeah, don't get too bogged down in those symbols. Okay, what could the enzyme inhibitor complex then do? Stay together, or it can decompose and go back to our reactants.
K negative I.
So K negative I would be our symbology on this. Okay. The other reason I'm bringing up the symbology is Sapling uses it for one of your questions, and I think they use Ki. Okay, so we're referencing the formation of the inhibitor complex or the decomposition of the inhibitor complex.
You can get some kind of product from that inhibitor and cause some kind of reaction.
So if it formed a product, then the enzyme's doing a reaction where it's forming a product, in which case it's not an inhibitor, it's a substrate.
So it'd be different.
It's a different substrate. So I would say ignore that altogether. You're making it more complex than you need to.
Don't go
Your
there.
substrate either goes through to make product, okay, or your inhibitor binds and prevents that reaction. We aren't getting specific on what that specific substrate is. We're just saying a substrate binds, makes product. Okay? Or an inhibitor binds, no product. Okay? So let's think about Vmax. What did we say Vmax was? Okay. So if we looked at a curve of rate versus our substrate, right, we'd have this line. Where's Vmax? Okay. This was our Vmax. When do we achieve Vmax? All the enzymes are saturated, which would be when? You want to add to it?
I would say when all the binding sites on the enzymes are saturated.
Yep. How do we bind all of those binding
You
sites?
get lots of substrate.
We have lots of substrate. Okay. Let's say we have a stupidly, ridiculously large amount of substrate. What would the effective concentration of the inhibitor be?
It wouldn't have an effect.
It has no effective result, which means what happens to Vmax?
So it's not affected by it.
It doesn't change. Vmax for a competitive inhibitor should not change from the standard substrate.
If there's a lot of substrate and not a lot of.
But
But
Vmax
that's
is.
but that's what this curve means. That's when you achieve Vmax, is when you have a ton of substrate. So if you have a ton of substrate, we're pretty much saying your inhibitor is irrelevant. Okay? So your Vmax for a competitive inhibitor
Shouldn't be affected.
should never change.
Well, that's nice. Let's just stay with Vmax. Let's just hang out there.
Okay. So now the harder one is Km. Okay. I did have this straight. So let's see if I can do it. Okay. So what happens to Km with an inhibitor? What would happen if we looked at our enzyme concentrations? So this is where I first went with this and ultimately why I screwed up. If we have a competitive inhibitor, what would happen to the concentration of the enzyme?
Doesn't
It would go down somewhat because.
It's going to have to go down.
The inhibitor would take some overload.
The inhibitor reacts with the enzyme, which means what happens to the enzyme concentration?
All right.
Your enzyme concentration should go down. Well, if the enzyme concentration should go down, what would we expect to happen to Km?
Go up.
Okay. If E gets smaller, what happens to Km? If the numerator gets smaller, what happens to Km?
It gets bigger,
Okay, let's take some numbers.
smaller. Like I
Let's
said,
take
smaller.
100 over 1. What happens if I make that 100 50?
All
Goes down.
What happens to your Km? the Km would get smaller. So if our enzyme concentration goes down, we might say, well, then Km should get smaller.
Wouldn't your ES also get smaller?
There's the assumption that I screwed up when I first looked at this. If the enzyme concentration goes down, we would expect Km to go down as well. But what happens to the enzyme substrate concentration?
It goes down as well.
It's also going to go down proportional to how much this one went down, which means
There's no effect.
there would be no effect looking at those.
Okay.
Okay.
So
So what we need to do is not look at the concentrations, we need to be looking at those rates. Okay. And that's where this becomes tricky.
Who's gonna go down?
Why should K2 go down?
Because ES goes down. It does go down proportionate to E, but it goes down because it's being taken to EI.
ES doesn't determine your E concentration.
Those are constants though, those
Those
shouldn't
are
change
Constants.
your concentration.
So what we need to determine is how those things would affect. Okay. So our initial assumption was that E would go down, which means Km goes down. Okay. And the reason I'm repeating that is because the opposite thing happens. Km increases. Wait a second.
Yeah, because you said KM was the.
No, Km is
the
unchanged.
binding
No, it increases. I was right.
energy. Wait,
Oops.
say that again?
Km increases. It does the opposite of what we would have expected. Okay, so why would Km increase? Okay, well, what things are changing in here?
Because with the inhibitor, you said if the higher the KM, the less binding affinity. So if there's less of the,
I didn't say there's less binding affinity. If there's less binding affinity, you're saying Km,
goes up,
oh, it goes up, yep. Yeah, so
And
we
it's
have
still-
less binding affinity.
and that would mean, and
So
that would make sense.
Yeah.
Because there's now an inhibitor, so there is less binding affinity.
the enzyme can't hold on to the substrate as tightly because there's an inhibitor preventing it from binding to the substrate.
Right.
I hadn't heard of it that way. Good
Is
way
that
to do
how
it.
that
No, it
works,
works.
right? Okay.
It works. So your Km actually increases in this case. Why? Your affinity, so remember what the Km was. It was the binding affinity for the enzyme for the substrate. Okay. If there's an inhibitor there, what happens to that affinity?
Goes down.
Okay. The affinity has to decrease, which means your Km
It's gonna increase.
increases, because remember there was an inverse relationship between those two. Okay. So K2 and K minus 1 are effectively becoming larger than K1. Okay. Or we could say it differently, K1 gets smaller. Why should K1 get smaller?
Because of KI. Oh, you said that you can't. Oh,
Okay. What happens in that relationship to form the enzyme substrate complex? What's going to happen to the rate in that step?
decrease.
It's going to decrease. Okay? Which means our Ki necessarily had to decrease. If Ki decreases, what happens to Km? It gets bigger. What happens to K2 and K minus 1? Okay. I have less product being formed because the substrate or the enzyme is being killed by the inhibitor, which means what's happening in that last step? It's slowing down. K2 gets smaller divided by a bigger number, and we get an even bigger thing. I'm not sure I did that right. Okay. Our big memorization is that our Km is going to get bigger. The affinity for the...
KI or K1 gets smaller. So they're both
So-
getting smaller.
K1 gets smaller, yeah, so K2 has to get bigger. Okay.
Or does it
That
stay
rate,
constant?
or it could stay
I thought
constant.
you said it didn't matter, that ES to P is gonna stay this, like that
So it's-
rate is gonna,
Deciding how we look at each of those constants in those relationships, yeah. So the effective relationship between them. Your denominator has to get bigger, get smaller, and your numerator has to get larger.
okay.
Okay.
But in essence, we just need to know that Km gets bigger than the inhibitors are.
There's your end argument. Km gets bigger. Vmax,
Because the inhibitor is only affecting, in that equation, the only place that the inhibitor is affecting is the K1 rate. Everything
Yeah.
else goes on its own, and that, it doesn't, the inhibitor has nothing to do with, it's only K1 that it affects.
that's probably the best way to look at it. Your K1 is the only thing that's affected, which means K1 gets smaller. As K1 gets smaller, Km gets
Bigger,
bigger.
okay. That's good.
Okay. And you can be skeptical on it. I'm fully okay with that. But that is the relationship you need to pick up.
I don't know, you would think that if K1 was getting smaller,
K1's getting bigger.
or bigger.
Sorry, smaller. Ah! They switch, and that's the other thing that I'm trying to
You think
keep
there
in
would
track.
be kind of a proportional change to K negative 1, since they're kind of opposite rates, so if one is changing, you think that would make.
So even if they're proportional, this is an addition here.
Right.
Okay. So if this gets smaller, this may get smaller, but this number is still not changing proportionally to this one. Whereas in the enzyme concentration relationships, there, since it's all multiplication, it's a proportionality change. You'd get no effect. When you look at your rate constants, since it's an addition, you don't get the same proportionality. So as K1 decreases, K minus 1 may very well decrease, but your proportionality doesn't hold. Okay? So could it get worse? Of course it can get worse. We can come up with two extra ones, non-competitive, or believe it or not, uncompetitive. Okay. So your non-competitive inhibitor. Okay. Any ideas what the non-competitive inhibitor would do?
They don't bind to the substrate binding site, they bind somewhere else.
It binds somewhere else in the enzyme. Okay. But we have two possible types of inhibitors that could bind somewhere else in the enzyme.
Oh, those are two different things?
Those are
Not
two
just
different
names,
things.
but
No, those are two different things. You get non-competitive and uncompetitive. Okay? They both have the same general idea. An inhibitor is binding somewhere else in the enzyme, preventing product formation. So now the question is, what is the difference between those?
Non-competitive means that if it binds, it does change the active site to not allow the substrate to bind.
So in one case, the inhibitor binds, okay, changes the enzyme so that we can't form the enzyme substrate complex.
So it has the same effect as the competitive inhibitor. In some
A
ways.
similar effect,
Yeah.
but not the same.
Okay.
Okay. What happens in the other case?
What kind
No
of
change, but
picture, it's similarly shaped, but not exactly shaped, so
Oh, your inhibitor is still right here. It's all a question of what part of the reaction you're shutting down. Okay. In our competitive, we shut down the first part.
So maybe the uncompetitive
Okay.
is the product improvement.
So in our non-competitive and our uncompetitive,
It allows the
one
substrate to
option,
bind, but doesn't allow it to finish.
there it is. Our inhibitor binds to the enzyme and prevents the substrate from binding. So we prevent that first step. In the other case, the inhibitor can bind either to the free enzyme or to the enzyme substrate complex. In either case, it prevents product formation.
And if it binds to the ES, does it hold the substrate and not let it leave?
We aren't even bringing that into the situation. So as long as the inhibitor is there, it can't form the product. So then you're probably in a situation of either forming the enzyme substrate with inhibitor, so you're at an ESI state that could either go to EI or to ES. Or EOR. Oh. Sorry, I thought it was funny. Okay. So now the question is, how do each of these things affect? So one of the things that's going to be important is making sure that we get those definitions nailed down correctly. So I'm going to draw here real quickly so you can't see what I'm doing on the back end. Our non-competitive binds to a site other than the active site at any time during the reaction. Okay. So non-competitive, the inhibitor can bind at the beginning, to form your EI, or it can form after the substrate has bound to then form an ESI. These reactions are now all in equilibrium with each other. Okay. Which then means you're going to have all sorts of other added layers on top of that. So that is your non-competitive. Inhibitor at any time.
the non-competitive puts the entire equation into equilibrium, prevents
preventing product formation. Your uncompetitive, okay, the inhibitor binds at only the enzyme substrate. So if we color-coded that, so in our uncompetitive, we only bind to the enzyme substrate complex. Okay. Again, preventing product formation. So each of these cases prevents the product formation. Okay. Interestingly enough, what you'd initially suggested was the inhibitor bound to the enzyme preventing the formation of the enzyme substrate complex. Neither of these two explanations match that. Okay. So is there a potential another one that could show up as a potential reaction that we could be looking at? Yeah, wouldn't that be lovely? Okay. Okay. And actually, that does show up. That one is actually called an allosteric inhibitor because it's changing, it's preventing the substrate from binding. Okay, which is chapter 7, which adds a whole nother crap storm of kinetics and math into what's going on with it. And we'll look at that again. The issue with that is because we're now changing the structure, which affects the binding, your curve, instead of being a nice standard enzyme curve, being like this, was what? It was sigmoidal, which means all of this work that we're doing in Michaelis-Menten goes out the window when you drop in allosteric inhibitors. Okay, because it doesn't match the standard curve that we need for a Michaelis-Menten expression. Okay, which, fun story, we still look at a Km and a Vmax, but we can't call them Km and Vmax. We have to call them something else because they aren't Michaelis-Menten expressions. They aren't derived from that. Okay, so now that we've got an idea on what these inhibitors are doing, let's see if we can predict the answers out of these. So let's take a look at our non-competitive inhibitor. Okay. It can bind at any time. What's going to happen to our Vmax? I'm going to cheat.
Cheap too. It says it decreases.
Okay, so our Vmax decreases. Why should it decrease?
Because there's enzymes being taken out of the equation.
We can't form our product, period. So think again with our, of course I had to delete that drawing. If we looked at our standard enzyme reaction, why would Vmax decrease? This was our curve. When did we achieve Vmax?
And all the enzymes were saturated.
When we had maximum substrate concentration, our enzyme was completely saturated, okay, with substrate. But what's happening in this case? Our enzyme is being removed by an inhibitor in the system. Okay? Which means even if I form the enzyme substrate complex, it still can't go to product because the inhibitor is preventing the product formation. Which means, what should happen to Vmax? It should lower. I saw the look, so let's try it again.
You get no product whatsoever?
It's not that we have no product. So remember, we're not pushing it to the extreme where we completely remove the reaction occurring. If we go to maximal substrate concentration, we've then removed the effect of our enzyme and we're now all in the enzyme substrate complex. Okay? In the case of a competitive inhibitor, they were both competing for the exact same site. So if we've saturated our solution with so much substrate, well now the inhibitor has no effect because it has no place to bind. In the non-competitive situation, where is the inhibitor binding?
Different site.
A different site. So it doesn't matter that we have an incredibly high concentration of substrate, because even in the enzyme substrate complex, what happens? The inhibitor can still bind. Okay? Which means, in our non-competitive situation, your max rate will decrease because we are preventing it from forming product with the inhibitor binding.
So we were saying that substrate amount, right?
So if we go to our max substrate,
So we're saying that substrate will bind to the enzyme, and in some of these enzymes, you're also gonna have this non-competitive, or in all of the enzymes are gonna have this non-competitive?
some of those, not necessarily all of those.
Okay, so you still get
Okay.
some product in the ones where we don't actually have the
Inhibitor.
okay.
But some of them have the inhibitor,
Right.
which means what happens to your rate?
So it's just gonna go down.
It's going to have to drop, proportional to how much enzyme and inhibitor you've got in there. But it's still going to drop. Okay? And we don't care necessarily by how much. We're just saying it drops. So in this non-competitive inhibition, stupid eraser. Let's go back to our curve and attempt to draw these things out. So we'll go black. This is our standard line. This is Vmax. Now if we look at our non-competitive, our Vmax should drop. Okay, it will be somewhere lower.
Conceivably, if you add the enough, all the way off, or
If you added enough inhibitor, yeah, it could theoretically flatten all the way down where you don't get any reaction. But that's going to happen in all cases.
So then will that difference in those Vmaxes give you the concentration of the non-competitive inhibitor? Because you would know.
You might be able to come up with a concentration gradient there. I would avoid trying to do more math than you have to.
Well, I would think
Okay. So now the question is, what's going to happen to Km? All right, it stays the same. That's fair. Why does it stay the same?
it's all affected. Because K2 is also gonna now be affected, where before it was.
Everything gets affected. Okay. So all of those end up having some effect due to the inhibitor.
So does Km remain the same?
And actually we can switch that up a little bit more. We could look at it as there's really no big effect because the substrate can happen bind at any given point. Okay. So our Km ends up being unchanged.
but if Km is,
Because this is the binding affinity for the substrate. Well, the substrate can bind at any given point with the enzyme, which means
No effect there.
there's no effect on the binding affinity for the enzyme for the substrate. It should stay exactly the same because the substrate can bind at any given instant.
So this one non-competitive, it doesn't make any kind of alteration to the enzyme so that the active side is.
Exactly right. It does not do an allosteric effect. It does not change the structure of the enzyme.
Non-allosteric.
Okay, these are all non-allosteric. So our Km should not change. So let's go back to our black line and define our Km. So if that's Vmax, 1/2 Vmax is roughly there, which then means this is our Km value. So if I need to draw on my red line, half of my Vmax for the red line is somewhere in here. It must hit there. Why does it have to hit that point?
I thought it had to be the same,
Km has to be the same.
right?
Okay? Km is the substrate concentration at when you are at half Vmax. On this new line, we have a different Vmax, which means our half Vmax changes,
Okay.
which means the Km has to still be on that axis.
Same substrate concentration, different, whatever the rate is.
Different rate.
Right, okay.
Okay? And this line not intersecting down there is bothering me now.
X, different Y.
So our curve ends up looking more like this. That's close enough. Okay. So our Km for the competitive, or sorry, for our standard kinetics, okay, and our non-competitive end up being the exact same. So Vmax drops, Km stays the same. Okay, and again, this gets confusing because everybody goes, well, shouldn't it be the same point? It's not the same point because your Vmax changed. Okay? Freaking hate this part. Okay. So we ready for the next one?
Yeah, let's go.
Okay, non-competitive inhibitor, because we already know Jimmy's going to cheat for us. I'll just tell you your answers, and then we'll reason through them. And our uncompetitive, both Vmax and Km decrease. So let's deal with our Vmax. Why should Vmax decrease? So we're now looking at our purple line. Why should Vmax decrease?
Same reasoning.
Same reason as we had with the other one. Yeah.
It stops K2. Or
The inhibitor binds and it prevents product formation. Okay. So we would still expect Vmax to decrease. If I go to maximal substrate concentration, all of it converts to the enzyme substrate complex. The inhibitor doesn't care about the substrate binding. It can still inhibit. Okay. So Vmax should still drop. Okay. I'm going to draw it just a little bit lower than our first one, just so that we have it. Whoops. Just so that we can see that line, but it's the relative distance of these changing is irrelevant. Okay. Does that make sense? You understand what I just said? Okay. We just want to see that it is changing. Okay. The next part is that we said Km also decreases, right? Okay. So why would the Km also decrease? So our binding affinity decreases.
Because of Vmax, well, no, because you said that was
No,
the same
because that
amount.
didn't happen in the other case. So why did the Km decrease?
Because the inhibitor is only affecting the enzyme substrate complex, not the formation.
The inhibitor only affects the enzyme substrate complex, which means it's really only affecting K2 and K minus 1 at best. It doesn't touch K1. Okay. So if K2 gets smaller because we can't form product, what happens?
Km goes down.
Shoot, because it increased, didn't it? No, it decreased. Oh, we did that right. Whew, thank God. Okay, this is that part where I'm liking it. Okay, the K2 decreased because we can't get that reaction to occur. If K2 decreases, Km decreases as well. K1 is not affected because the inhibitor can't bind to that first enzyme. Okay. How would we draw that now on our curve? So if we go to our half Vmax now for our purple line, okay, it's good that I crowded it all in one tiny little spot.
It's okay, it has to go to the left.
Km has to go to the left, so I'm going to make a line there and say that's our Km. So we need to intersect about there. And we'd get our new Km.
Well, yeah, well, how come your Vmax wouldn't be around the same as well as the other one is?
So remember, the height of those Vmaxes is irrelevant. All we're trying to do is note their change relative to the black one. Okay. So if I did the purple one same as the red, that's fine. They'd then be overlapping. I'm just trying to show the difference there. Okay. So that was time for class to end. Kind of our hand-wavy approach to all of those summaries, looking at how those things approach and kind of going back to the equation saying, okay, how does that affect? Okay. And you may not like it. Fair enough. I'll try again on next Tuesday because we won't be in the library, or we'll be in the library this Thursday, to kind of go through that again and see if we can't make that a little bit more sensible when we break it down into the individual. Whoa. Oh, sorry. Forgot.
So just because there's less product being formed there, that changes the affinity of the binding sites? I guess that's what doesn't make.
I think it was
That
one.
last
Because
one.
it changes K minus 1. Because K minus 1 is dependent on the enzyme substrate complex.
I mean,
So K minus 1 and K2 change, but K1 does not in that last case. Because with the inhibitor,
two is changing.
K2 will change and K minus 1 will change. Because they're both dependent on the enzyme substrate concentration, which with the inhibitor isn't there anymore.
So the inhibitor is gonna mean you're gonna form less of the reverse as well as less of the product?
Both of those will have some effect. Okay. Because we don't have the enzyme substrate complex anymore. Okay. That has disappeared from our system. So both K2 and K minus 1 will end up changing. Okay. These at best are hand-wavy arguments. Okay. Because ultimately it's coming back to all those equations that we drew out, which I think shows up. Yeah. Down in this, shoot, I didn't draw the systems with it. we have to look at how the inhibitor affects the equation and fold that into your Michaelis-Menten expression. Okay, and then solve for the, in case of the competitive inhibitor, your new Lineweaver-Burke plot. Okay, where you're introducing the concentration of the inhibitor and the Ki, the binding affinity for the inhibitor and the enzyme. Okay. That is your strict way of looking at how it affects everything. That requires a whole bunch of mathematics and approximations and not approximations, assumptions, I think is the word I'm looking for, that are not clearly outlined at all in the textbook. Okay. With them gone, it makes it very difficult to figure out how they're coming up with this expression. Okay. So what I expect you to be able to do is this. You need to be able to define what a competitive inhibitor is, what a non-competitive inhibitor is, what an uncompetitive inhibitor is.
And how does
Then, how does it affect your Vmax and Km? Because the Vmax and the Km are our enzyme reaction with the substrate. Okay. What does the inhibitor do to change those values? Okay. So the rest of those next sequence of slides are looking at the variety of plots. How does that affect your lines? How would you interpret everything? Okay, and we'll walk through that, but we did already effectively talk about that by looking at our standard enzyme reaction curve. Okay, and we predicted what our Vm and Vmax would be. Sorry, Vmax and Km would be. You'd then just be translating that across to a straight line curve. Okay. So we will walk through those again. You'll notice that we also have one last one that Sapling brings in. The textbook does not, so we'll mention this one. What's the issue here? A mixed non-competitive inhibitor. Okay. This is binding at an active site at any time during the reaction that might prevent substrate binding. Okay. Whereas in the other cases, it completely prevented substrate binding. Here, it might. Maybe it prevents it from binding, maybe it doesn't. Okay, good luck with that one. Okay, so we'll look at what happens to that curve. It becomes all sorts of weird. Sapling does ask a question on that. You got a little hint down here. Okay, your new line would intersect on the left-hand side. So I'll leave you to kind of see what happens with that. Okay, so we'll walk through that on Tuesday. We definitely have to stop.